We need to create some tools for the final project. So looking at the slide block, we're going to have a T-slot, and we'll go with a T-slot cutter because of the neck down on the shaft. A woodruff cutter isn't really going to be that big, and with the arc, because usually you're cutting on a shaft with the woodruff, are really not going to have that much clearance. We're also going to need to set up a T-slot, and since we're setting up tools, we'll go ahead and create a thread mill, single point thread mill, and then probably come back and while we're going through that process, do a multi-point if you are picking a specific thread to the thread mill. All right, and then in the process, we'll go ahead and set up a tool library so we can reuse those geometries, tool geometries for our process. All right, so when you download, take your pick of parts. The solid model. This should be old enough, a 2014 or 2016. I'll double check and make sure that file loads correctly. And then the Parasolid is an X_T, and the IGES should be a wireframe. And then, of course, if you care to draw it yourself and stay in 2D, that's fine. Pick whichever one you're most comfortable with. All right, so I'm going to fly this out of the way real quick so that we can get started. When we're going through this process, the first thing to setting up a tool library is we need to be in the module or the machine type. So we're going to pick the mill and go ahead with the Haas tool group. I'm not really worried about setting anything up. We're going to come over to the tool manager, and most of what we're going to be doing takes place in here. All right, so with the tool manager, let's go ahead and set up as if we were doing a side mount tool changer, or we had a situation, the tractor type tool changer, where we're going to load up a certain amount of tools and even get into a situation where, as we can do tool checking, that we would be able to replace tools within the group with other common other tools of the same size and type. Alright, so I'm going to create the filter, and we're going to pick for none, and I'm going to switch it just to end mills. And so kind of the standard, let's make the filter active, standard tool group is, as we're creating this, I would start with 1/2 inch being most common. And I did not go through the process of creating these 1, 2, 3 in sequence. So let's go ahead and check the difference. If I double click on that and then finalize the properties, those will all change to 1. All right, we can certainly put more information in there. So let me go ahead and check that one. And this is where the tool settings comes in. We're going to assign tool numbers sequentially, warn of duplicate numbers. Alright, and then I'm going to jump back into the tool manager. And let's see, I'm going to go to a 3/8, and we're just going to add by common. And now instead of picking the library number, it's going to add these in sequence. So if I was loading these up into my side mount, then 1, 2, 3 would be in order. Alright, so then a 1/4 inch, we'll go to an 1/8 inch. And probably don't need anything too much smaller than that. Let's go back into the filter, other tools that I would like to have in my custom tool library. If we were to do a face mill or a fly cutter, now this is where we would start to customize the geometry a little bit. So let's go ahead and see what's available, and we'll turn the filter active again. So let's call it a 3-inch face mill, and I will add it. And I'm not changing anything in the mill inch library. I want to do this in the library that I'm creating. And so a fly cutter would have the cutting diameter 3, secondary diameter, if there's any kind of angle to the insert. So let's see, where's that one? So if you have a 45 or a 60 degree, then it would be to the tips of the inserts. So I'm going to say that this one is going to stay pretty much at depth, tip angle, diameter, tool diameter shouldn't or don't intersect. Let's see if 10 thousandths makes it happy. I'm not sure what it's going after. We basically have a square. I'm thinking of a single insert fly cutter or brazed insert, like a brazed lathe bit holder. Overall length, we'll get to, yeah, the 2 inches is okay, but the cutting length, it certainly won't be over ½ an inch, so we'll bring it down. Let's see what, that one's not going to, oh, shoulder length exceeds tool length. Okay, so overall length, let's go back to 2, and then we'll give the shoulder length a 0.4. Alright, so looking more like a fly cutter as we go through the geometry. Tip corner treatment, we'll have a little bit of a radius. Shouldn't be any angle. Now let's stay with the chamfer, and we'll just leave it at 45 degrees so it has some geometry in there. Finalizing the properties, tool number for this is going to be 5,000 surface feet per minute. Number of flutes goes down to 1, which should affect our feed rate. If we go into the recalculate, well, that's slowing it down quite a bit. So let's go back to the 1,000 surface feet. So 1,000 RPM, 5 inches per minute. That's still a little bit on the slow side for the 3 inch. So let's see, where are we getting RPM at? It's not outputting the RPM just yet. Feed per tooth of 4 thousandths. So 1200 RPM, we'll try it at 10 inches per minute. Plunge feed rate, there it was, 1528. And we'll just do a little rounding there so it's not. Alright, 10. Material is carbide. Clockwise rotation. And then if we had additional information, we could put that into the mix. Percentages of step overs for roughing and finishing. So typically we'll be finishing with this. So let's go with 70% step over and full engagement. So if we do a zigzag, it will use 70% of the tool. All right, and we can refine that as we go a little further into it. So let's see, what else would I like to have in my default tools. Turn the filter off, and let's see if we can find an engraving tool. All right, so we'll turn that back on. All right, turn the face off. There we go. So 1/8 inch engraving tool, corner radiuses we can't really see there. Not much corner radius. Let's say some of the nice engraving tools have about 15 to a 30 thousandths end radius that kind of has a scooping action to it. So let's just go ahead and define it. 0.36. We'll get one into the mix. All right. So from that point, the filter is still active, and I'm making a point because whenever I set this up, my practice run ended up with a bunch of duplicates because the filter was active. So let's go ahead with looking for the dovetail end mill. Alright, so we'll go ahead and hit OK. Nothing shows up in that mix. Now if we open other tool libraries, there may be something mil-inch, millimeter. Those are tool holders, different databases, so really don't have too much to go over to. So we'll just go ahead and create these tools. Alright, so this becomes my standard. If we were doing a lot of the dovetail, I could add those in. Since haven't, let's see, we cleared that out on the filter. So I want to create a new tool library, and I probably already have, maybe not. Let's go with the My Tools, or more specifically to a machine. I would probably set this up. I'm going to run the Haas tool room mill, and then I can set the RPMs and start to get a little more refined as to 4,000 RPM max, 7,500 max RPM, 10,000, 12,000, yeah, whatever we're working with. If this is going to be a tool library that I'm going to come back to often, and I really don't care about numbers, then I can do the same type of thing. So we'll go ahead and make sure that the filter is not active. And so the problem, let's go ahead and do this once. The problem with the filter active is that when I highlight all these and send them to my library, nothing's there until I turn the filter active off, because the last one I did was the dovetail, which didn't have any geometry, didn't have anything created for it. Alright, so filter active, nothing. If I keep adding those down, last time I ended up with 2 or 3 groups of tools 1 through 6, so I don't need those duplicates. Alright, so for the current tool group, let's go ahead and create a new tool, and we're going to tell it to, let's start with the dovetail. And no particular order, just whichever one we decide to go first. I don't know that I have a preference on order of operations for this, so we can set it however we need. But the main one here is 7/16 is our depth, our length of cut, and we have 1 1/4 inches to work with, which means this is going to be pretty close to 1.5 inches on the length. So we need to kind of keep that in mind on our parameters. Oh, shouldn't have got rid of that just yet. Okay, so I go over to MSC or to McMaster, Granger, take your pick of favorite tool providers, and I typed in dovetail cutters, and we're kind of looking down through. You can go with brands. We can default to the included angle of 60 degrees. I already picked a cutting width of 7/16. At least I thought I did. Alright, so 7/16 width, 1/2 inch shank diameter, and so those are the three critical pieces of information that we need for this cutter. 1 inch diameter, and usually what I do is I'll set that between 5 and 10 thousandths oversized because of the variation, deflection, materials that we're cutting. I want to comp this in to bring it to size. Bringing the dovetails to where they have a nice smooth fit into geometry is always difficult. So you know, we can count on clearances, we can count on the locking mechanism to do part of that for us, but I don't want to start off oversized. So we're telling it that it's a dovetail mill. We're going to define the geometry as a 1 inch. And overall length was 2.5 inches, and the cutting length 0.4375 7/16, and the taper angles, this is showing us the half angle, so 60 degree would be our 30 degree angle. And whether this was an insert style cutter or the high-speed steel standard cutter. This gives us our geometry that we're going to preview to. So it was a 1/2 inch shank diameter, so that all looks pretty good. We're going to be cutting aluminum, so I haven't really set material. This one's going to be high-speed steel, and surface feet per minute at 200, feed per tooth at about 1,000, number of flutes. This is probably either going to be 6. It doesn't, based on size, it might be 4 flutes, but more likely it's going to be 6. So we'll go ahead and bump that up a little bit. Feed rate of 5, maybe a little fast. I'm going to back that down until I get a good number. And the plunge rates and the retract rates, I don't want to be too aggressive. Spindle beat at speed of 750, that looks pretty good. And dovetail cutter, and so roughing XY step percentage, we're at 1 inch, so really 10% would be 100 thousandths. That may still be kind of aggressive depending on the material and the depth of engagement. So I want to get that started. And let's see, the rough Z-step calculates the size of roughing. Well, that's as we're moving down. Typically, we're not going to move down this angle, although if we could do the volumetric, removing the same amount of material each pass, that would be a good way to go. Alright, so since I added it to my library, I need to go ahead and bring it up to the current library. So maybe didn't mention, everything up here is our current library. This is the saved library. So as we're generating these are put in, and I can kind of reorder, repurpose these as needed as I use this library, either for different projects or for different machine tools. Alright, so let's go ahead with another tool. And, well, so I clicked down here before, so let's see what happens if I click up in the current. So we're going to go with the slot mill. So looking back, we're kind of focused on the dovetail, so we're going to come back to the slot. We have 1.5 inches of width, 15/16, so that's kind of the smallest shank diameter that we can get down through there. Of course, we'll be taking an end mill and roughing through, so this would be a good place for an area clearance, having the two individual chains, so that it can nibble through there on the trochoidal. It could also be a pocket where we overrun the ends. Either one of those will get that opened up to where then we can bring the T-slot cutter in and make several passes, and with enough extension make sure that it clears so that we can generate the slot. So let's look for an 11/32, and so I already did a search for T-slot cutters. Looking down through the cut diameter, not so much of an issue as the cutting width. So 5/16, and one of the issues may still be that when we look at cost or the size of these cutters, then we want to find the most efficient cost and cutting action. So I'm going to go with the 5/16 to start with, and then we want to be able to compare it the next size up. And did it limit me out on the width after I did that? Let's see, there we go. Let's scroll down, and we'll also do the 21/64. And if I pull up my calculator, equals 328. So that's pretty close. Our 11/32, jumping back over here, it should be 34375 as our decimal equivalent. So we're under that with the 328. Oh, and I jumped out of the window there. Alright, so let's see what we have to pick from. So 3/4 inch shank diameter is smaller than the 15/16. Alright, so we have those to pick from. height of 21/64, and then let's see. Well, not seeing very many 5/16. Yeah, it's still filtering for the 5/16. So. Alright, so uncoated, staggered tooth. Alright, so straight tooth, staggered tooth can also play a little bit in the Joyce's cutting action. Looks like there's quite a jump in price though, going to the 5/16 cutter, and just a little bit shy of the 25-30 seconds. Well, looks like they're all pretty much going to stay the same. So the nice thing about the 21/64, the 328 size will allow for just 5/1000ths off the floor, and then a little cleanup on the upper and a little cleanup on the lower to finish out the part. So we'll set up the tool, and on the slot mill, then we're going to define the geometry. Our cutting diameter was 25/30 seconds, so let's see if we can just do the math here without having to go back into the calculator. So 781. And let's see, neck diameter. No, that doesn't. Cutting diameter 781 with a neck diameter of 3/4 for a 3/4 inch or 3/8 inch bolt. That seems that's going to be pretty close. We also have to consider the undercut on these. We're 1.5, and then the 15/16, so that would be a 1/4 inch engagement, plus another would be about 281 on the depth of the slot. So now let me fly this in, we'll double check. So 1 inch cut diameter and a 5/8 inch shank, 5/16 height. So that would go to 5/16, which divided by 2, that would put us at the 156 depth, so that's still not quite deep enough. And then that one's getting pretty thin. That's a little bit, we're not going to be able to, as we get smaller on that neck diameter, we're not going to be able to run this tool as hard, but that puts us up at 5/8, which would be 5/16 cut width and 5/16 engagement. That may be the one we need to go with. Let's see, a 15 millimeter, that should be 590. So there again, not enough undercut. So, well, we'll come back and double check that one. Concern is that we're not running into anything we don't want to run into. So 1 inch on the cutting diameter. Length is overall length was almost 5 inches, so I'm just going to round up. 4 and 15/16 doesn't really matter. And the thickness was 5/16, so 3125. Shank diameter 0.43. I don't know that I need to go out to the 4th decimal place on that one. And shoulder length, let's see which one is that. So there shouldn't be anything above that, so I think that's okay. Alright, so leave the tool properties. High-speed steel, so 200. Well, let's switch back over. 200 feed per tooth. There are 4. Now this one's showing 8 flute as a staggered cut. And then the Spindle speed, yeah, let's start with the 1000 RPM, see what that does. That bumps it up a little bit. And if we don't get too crazy with the engagement, so I still don't want to get too aggressive with that feed in, feed out. So let's keep it at the 764 for now, and the feed rate even at that. Let's bump it down just a little bit. All right, and once we see how it gets engaged, then we'll come back and revisit those numbers. All right, so this was a slotting tool or saw. Manufacturer name, and this was well, there's some to pick from. Since that's not in there, we would have to add it. I'm not going that far into it, so 1 by 5/16 by 7/16, and then if we want to put in a part number, okay, so it gives us something to reference back to. The roughing XY step, I'm going to stay down at 10%. That 30, let's see, at 1 inch, that's still 100 thousandths. With that 7/16 shank, I'm a little concerned. Maybe we'll go to 5%, 50 thousandths engagement to start. And then as we step down, the strategy is going to be to calculate. All right, so that puts us into the to the mix, and notice that it was added at the current tool level. So we need to make sure that it goes to our tool library. All right, so any other tools that I would use commonly, I can add to this library, and we'll just keep accumulating numbers. So drill bits, taps, things that I use all of the time, I would go ahead and put in here. And then when I go ahead with the OK, it's going to say, do you want to save the changes to the library? Yes, now they're part of that library. I go back, and when I first load up, and it goes back to the mil inch, I can open up my library, and then it will come back over here to the ones I use commonly. If we go back into it's either going to be the control definition or the machine definition, we can have it default to this library, more common. All right, so one more is we need a thread mill. So either way, we're going to create a new tool, and we do have the thread mill, and it defaults to a multi-flute thread mill. And what do we, let's go with the biggest thread per inch that we think we can cut with this, which would be an 8. And the outside diameter, we'll go with the 0.75, overall length of 2.5, and then the cutting length would be 0.125, which matches our 8 threads per inch, being 125 pitch. Shoulder length, 1.5 inches. Don't really care about those. We can come back 0.375 and 0.375 for the steps. That still looks pretty good. Tool number 9. Now this one is going to be carbide, so surface feet per minute. I'm still going to start off a little bit on the low side at 600. Would probably end up a little bit closer to 800 on this one, so I'm just going to round the spindle speed. Number of flutes is 6, and feed rate, still starting off on the slow side, maybe not 100. Okay, got those extra zeros in there. Alright, so thread mill, And so 0.75, and then shaft diameter, or shank diameter 375. Alright, and if we had a number for engage for the total part number, we could put it in there. I'm not going to put steps. I would like to have this slow enough that it would be able to engage and run the full cut. Alright, so again, since it's on this group, I'm going to go ahead and add it. And then again, when I hit OK, so remember the filter, that was the only one that was added as the tub tail cutter, which is my filter setting. So if we were at all, then everything would be in there, but make sure to check that one. And we'll go ahead and accept, and then it will ask to save. Alright, so to engage the thread mill, we need to have some hole geometry. And this isn't really part of the final. I should put a hole through the middle of it and let you, well, let's see, there's a 1/2 inch ream. That would be close to like a 5/8 11 if you wanted to put a 3/8 inch thread mill in there. That's still pretty big. We need a finer thread, so I'll bypass that one. Alright, circle and center point. So I said we had a 3/4 inch tool. Usually we're going to do bigger threads. So the advantage of the single point is it's not tied to pitch, where a multi-point we would have 20 threads per inch or 12 threads per inch or 14, 16, 18, take your pick, but you're going to have a more dedicated. So let's say that I want a diameter of 1 1/8, and that is the major diameter. So 1 1/8 12 comes to mind. I think that might have been what I did on the acrylic pieces. So let's see if we can write a little formula here. 1 divided by 12 will give me smaller, so 1.041. For an internal thread, that is probably a little on the small side. We're going to end up being short, so I would rather err on that on the small side, and then come back later and find my machinery's handbook number, come up with the smaller minor diameter. If we were doing an external thread, then I would put it at 1 inch, and then the cut would be on the to the outside. Alright, so just as an example, I have the minor diameter. We're going to go with, well, normally with pocket, I'm just going to finish. Not sure what I clicked there. That was strange. Alright, so let's go with the chain geometry. I clicked one too many. Oh, I jumped out of it. I didn't pick anything. That was strange. Alright, I guess I haven't done that before. So I hit OK without picking anything. Alright, so we're going to pick the 1/2 inch tool. Now this is still set to read off of the default for the tool. So if I go back and we come up with a number defining the tool geometry, no cuts, we're going to turn this over to carbide. We'll go up to a little bit faster, 2 or 3 flute. Feed rate, that's a little, yeah, it's not too awful high at 1,500. Let's drop it down to 20 for those, and if we had a 7,500 RPM spindle, that we're kind of right there anyway. So we'll finish, and go ahead and accept. And then I had the TM machine set up, so it's defaulting back to 4,000 RPM. So all right. So I need to go back into that machine definition that we're currently using for the Haas, and I would need to program for the higher. All right, so cut parameters, we're going to turn wear on. In there, lead in needs to be a lot smaller, so maybe 30 thousandths, 120 on the sweep. Brings it back around. And don't really care about entering, exiting at the midpoint. Link parameters will give it a depth of -1 inch. And we'll go ahead and accept. And then I need to regenerate. Alright, so the 120, just make sure that it comes in a little bit off the wall and around. Alright, so we're away from the edge. So I'll go back to the top. Alright, so then the mill toolpath. Contour. I have to about where that one's going. So let's double check the chain. So it's to the outside and climbing. So let's reverse the chain and change the side. Okay, so we'll be climbing and on the interior. We'll pick up the thread mill. Alright, so since it's being defined to the tool, and then it ties to the numbers that I put in. Alright, and so climbing with the thread mill means that it's going to plunge at the center and then come back, start working its way out of the hole. And so let's see, I think I picked the wrong one. Okay, I always want it to be a contour, and in fact it still falls underneath the drill. Alright, so we're going to pick the point at the center. We've opened up the trim with the end mill. So toolpath type, drill, circle mill, point, helical bore, and thread mill. Alright, so then with the thread mill, now we can pick the tool. Well, not using the stock here, we're just going to go to the cut parameters, and it picked up the geometry, number of active teeth, 1, pitch of 0.125, start angle. If we wanted to tie it back to a location on the circle, allowance for overcut, no taper angle, so if we were cutting a pipe thread, it'd be about 1.4, 1.5 degrees, somewhere in there. We do want compensation at wear. This is an ID thread, and the major thread diameter is 1 inch. It's a right-handed thread, and machine depth direction is from bottom to top, which is what we set for climb milling. And let's see, lead in, lead out. We're going to start at the center, so yes, I want to plunge at the middle, have it feed over, and then start to make the cut. 100 thousandths entry exit. Now it's a 3/4 inch end mill with a 1 inch major diameter. Actually, I think we set that, no, we did set that as a 1 inch 12, so thread pitch is actually a little bit smaller. 1 divided by 12 should be about 83 thousandths. Okay. Alright, so we're going into that 1 inch 41 thousandths, so we have enough. We have over a 1/4 inch. Still, I don't know that I want to be that close. If it starts at the center and entry exit arc clearance, and it should come up above the part. All right, we'll leave it at the 100 thousandths. See what it looks like. Multi-passes if we need to rerun the toolpath. And then the linking parameters, thread depth. I cut the hole at a minus 1 inch. I probably don't want to go right to that, so minus 950. Even though we're touching off on the bottom of the thread mill, really, would not like to touch. Don't want it to touch the bottom of the bore. So even if I were to go 990, I want to have that little bit of clearance. And then let's go ahead and see what we get. All right, so feeds in, creates the helical spiral, comes out. All right, so this will work with our solid geometry, with the wireframe geometry. I didn't set up any stock, so there's not really anything to see here. So let's give it a 2 inch by 2 inch by 1 inch. And then when we set up for the simulation, so that first plunge there is going to be a little bit heavy. And we'll slow down a little bit. Alright, so main thing for the end mill was to have it be able to show those threads. Alright, so where I messed up here on the parameters is we have the thread pitch, and then there it is, the major thread diameter, 1.125. Alright, and then we'll regenerate the dirty tool pass. Yeah, I probably should have run both of them from the start. So let's see what it looks like when it finishes, though. So showing the 3/4 inch holes coming through, and not really picking up the thread geometry. There it is. Just had to pull it on the angle. So it is showing a little bit of the thread, but the hole not being opened up is a little bit strange. All right, so that'll give you some of the customizing, putting in tools, saving your tool library, and going through that process.